Welcome to our deep dive. Today, we're going to be looking at some elements that don't always get the attention they deserve.
Oh, yeah.
Non-metals and metalloids.
Interesting.
Yeah, they're really important, though. They're everywhere, like in the air we breathe
Right.
and the tech we use.
A lot of people don't realize just how abundant some of these elements are and how their unique properties make them, well, essential.
Yeah, for sure. So we'll explore those unique properties and see how they make these elements so essential.
Okay.
So let's start with a basic comparison.
Okay.
We always hear about metals,
Right.
but what makes non-metals different?
Well, it's all about contrasts. Think about a shiny gold bar, you know?
Yeah.
Easy to shape, great conductor of electricity. That's your classic metal.
Okay.
Non-metals are the opposite.
Yeah.
Dull, brittle,
Uh-huh.
bad conductors. Think of like a lump of coal.
Right.
You can really see the difference.
Yeah, so metals are like the stars of the periodic table,
Yeah.
and non-metals are more behind the scenes.
Uh-huh. That's a great way to put it. And then you have the metalloids.
Yeah.
The in-betweeners.
Oh, yeah.
Blending the lines. They have properties of both metals and non-metals. Makes them very versatile.
Like the multi-talented performers.
Exactly.
So tell me, why is that in-between nature so valuable?
We'll take semiconductors, for instance. Metalloids are crucial in this field
Okay.
because of their unique ability to conduct electricity, but only under certain conditions.
Oh, interesting.
Yeah, and without that property, we wouldn't have computer chips
Wow.
for smartphones and laptops and all that.
So if you're listening to this on your phone or computer,
Yep.
you can thank a metalloid. Incredible. Okay, let's focus on some specific non-metals.
Okay.
Where should we start?
Let's start with the most abundant element in the entire universe.
Wow. Okay, what's that?
Hydrogen. Colorless, odorless,
Okay.
and highly flammable. Quite the combination.
Haha. That is quite a combination.
Yeah.
You mentioned hydrogen being looked at as a clean fuel source.
Right.
What makes it clean? What are the challenges with it?
When hydrogen burns, it only produces water vapor,
Oh, wow.
so it's a zero-emission fuel.
Interesting.
The challenge is producing and storing it
Ah, I see.
safely and efficiently. It takes a lot of energy.
Yeah.
And the infrastructure to support widespread use still needs work.
So hydrogen has a lot of potential,
Yes,
but we're not quite there yet.
exactly. Now let's move on to another essential nonmetal,
Okay.
carbon. It's the basis of all known life.
Wow.
It exists in several forms,
Okay.
called allotropes,
Allotropes,
each with remarkably different properties.
like diamond and graphite.
Exactly.
They seem so different,
I know, right?
but both are pure carbon.
It all comes down to their atomic arrangement. Diamond, famous for its hardness,
Yeah.
has this rigid three-dimensional structure.
Okay.
Each carbon atom is tightly bonded to four others. Super strong, inflexible network.
Ah.
Graphite, on the other hand, is made up of layers. Carbon atoms arranged in a hexagonal lattice. Those layers are weakly bonded to each other.
So they can slide past each other.
Yes, that's why it feels slippery and it's used as a lubricant.
Wow. So just changing the atomic arrangement
Yeah.
changes the properties so much.
Completely different.
Carbon's a real chameleon.
Exactly. And of course, we can't forget about nitrogen and oxygen.
The air we breathe.
Yes. Nitrogen is a whopping 78% of the Earth's atmosphere.
Wow.
And oxygen, obviously crucial for respiration,
Yeah.
is about 21%.
We couldn't live without them. What about some other key nonmetals?
Well, phosphorus and sulfur are critical components of DNA,
Oh, wow.
RNA. Other vital molecules, they're crucial for energy transfer and biological processes.
It's amazing to think that these simple elements are the building blocks of life.
Yeah, it really is.
Now, before we move on, I'd like to talk about diatomic molecules.
Yes, the dynamic duos. These are molecules that consist of only two atoms of the same element, or different elements. We have 7 elements that naturally exist in this paired form. Hydrogen,
Okay.
nitrogen, oxygen, fluorine, chlorine, bromine, and iodine.
They're held together by covalent bonds, right?
That's right.
Could you explain how those work?
So in a covalent bond, the atoms share electrons to achieve a stable electron configuration. So imagine 2 atoms each needing 1 more electron
Okay.
to complete their outer shell. Instead of fighting over it, they share a pair.
Oh, so they both win?
Exactly, a molecular partnership. And these diatomic molecules are essential for tons of biological and chemical processes.
That's fascinating.
Yeah.
Okay, now let's look at the periodic table as a whole.
Okay.
and explore those mixed groups where metals, nonmetals, and metalloids all hang out together. I
Right.
want to learn more about those.
Groups 13 through 17,
Okay.
they're quite diverse.
Yeah.
Mix of metals, nonmetals, and metalloids.
Huh.
So you get a wide array of properties within each group.
So these groups are like the melting pots.
Ah, good analogy.
Of the periodic table, what kind of trends do we see in these mixed groups?
Well, one key trend is reactivity.
Okay.
It generally decreases as you go down a group. So, for instance, fluorine at the top of group 17,
Yeah.
super reactive.
Okay.
Iodine further down, much less so.
Oh, I see. So the elements at the top are like
Yeah.
the eager beavers,
Exactly.
and the ones lower down are more laid back.
That's one way to put it. Now, let's look at some specific nonmetals in these groups.
Okay.
We've already touched on the halogens.
Right. Fluorine, chlorine, bromine, and iodine.
Yep. Known for their high reactivity.
Yeah, they love to snag an electron.
Exactly. Complete their outer shell.
Yeah.
That makes them powerful oxidizing agents.
Okay.
For example, chlorine is used to disinfect water by oxidizing and destroying harmful microorganisms.
So they're like the guardians
Yes.
of clean water.
Yeah.
Any other practical application?
Oh, tons. Bromine compounds are used as flame retardants, to prevent fires from spreading. Iodine, of course, is an antiseptic.
Right.
And fluorine, added to toothpaste.
Oh, wow.
Strengthens tooth enamel.
So halogens are more common than I thought.
They're everywhere. It's amazing how we can use them for so many things.
Yeah, it really is. Okay, what else?
Let's move on to another interesting group of nonmetals.
Okay.
The noble gases.
Yes. Group 18, known for being unreactive.
Right. They have a full outer shell of electrons.
Okay.
So they're stable. No need to gain or lose electrons.
They've already achieved chemical nirvana.
Exactly. Content in their electronic bliss, but,
Yeah.
they do have some practical applications.
Oh, really? I thought they were totally unreactive.
Well, their inertness is actually quite useful. For instance, argon,
Okay.
used in welding, creates an inert atmosphere,
Oh, I see.
prevents the hot metal from reacting with oxygen.
So it acts like a shield.
Exactly. What other noble gases? Well,
Helium.
the lightest one.
Yep. Known for its buoyancy. Fills balloons and airships. Right. Makes them float. What about neon?
Neon. Famous for its glow. When an electrical current passes through it, that's what lights up those neon signs.
So each noble gas,
Yeah.
even though they're generally unreactive,
Right.
has its own unique uses.
Precisely. Okay, let's go back to the metalloids.
The in-betweeners.
Right. We talked about them being important for semiconductors.
Yeah.
But let's dive into how that actually works.
Okay, yeah, I'm curious about that. How can they be both conductors and insulators?
It's their electronic structure. They have a partially filled outer shell,
Okay.
so they can conduct electricity under certain conditions,
Oh, like when?
like when exposed to heat or light.
Interesting.
But under other conditions, they act as insulators.
So it's like they have a switch
Haha, yes.
to turn conductivity on and off.
Exactly. And that's what makes them so great for transistors.
Okay. The building blocks of modern electronics.
Right. Could you explain how transistors work?
Well, I know they use metalloids.
Right. So think of a transistor as a tiny gate
Okay.
controlling the flow of electrons. And by applying a small voltage to the metalloid material, we can open or close that gate,
Oh, I see.
allowing or blocking the flow of current.
So they're like tiny traffic controllers.
Haha, exactly. Directing the flow of electrons in circuits, the most common metalloid used for this is silicon.
Oh, okay.
Abundant, relatively cheap. And it has the perfect electronic properties for transistors and integrated circuits.
Now, remember you mentioned doping
Yes.
in relation to semiconductors. What is that?
So doping is when we add impurities to a pure semiconductor, like silicon.
Okay.
Those impurities change the conductivity of the material.
Oh, so we can adjust it.
Exactly. It's like adding a pinch of spice
Yeah.
to enhance the flavor.
To get the conductivity just right.
Precisely. And by doping silicon with specific impurities,
Yeah.
we can create regions with either an excess of electrons, that's called N-type doping, or a deficiency of electrons, P-type doping.
And these regions interact in specific ways.
Yes, to form the basis of transistors and other components.
It's amazing how we can manipulate these elements on such a tiny scale to create such amazing technology.
It really is. And it all comes down to understanding
Yeah.
and controlling these fundamental properties of the elements, especially those in-betweeners, the metalloids.
Okay, let's talk about the heavyweights now.
Okay.
The transuranium elements.
Right. They're the ones that come after uranium.
On the periodic table.
Exactly.
What makes them different?
Well, first of all, they're synthetic,
Oh.
meaning they're not found naturally on Earth.
Oh, wow.
They have atomic numbers greater than 92,
Okay.
which is uranium.
So they're like elements beyond uranium.
Exactly. Created by humans.
What else is unique about them?
They're all radioactive,
Oh, wow.
meaning their nuclei are unstable.
Okay.
They decay over time,
Mm-hmm.
emitting radiation, and they're usually made in nuclear reactors.
Oh, wow.
Or particle accelerators.
They have such cool names, too.
I know, right?
Neptunium, plutonium, americium. Sounds like science fiction.
Haha, they do. So what are they used for? Well, plutonium, for example.
Eh?
Key component in nuclear weapons.
Wow.
Also used in some nuclear reactors. For power generation, americium is used in smoke detectors. Curium is used in research and medical treatments.
So even though they're radioactive,
Yes.
potentially dangerous,
All right.
they have a lot of important uses.
Exactly. But it's important to be careful with them.
Yeah, for sure. This deep dive has really shown me
Yeah.
how important nonmetals and metalloids are.
They're essential, even if they don't always get the attention they deserve.
They're like the unsung heroes,
Haha, I like that.
quietly shaping our world.
And their story isn't over yet.
Yeah.
Who knows what we'll discover next?
Each group on the periodic table, it's like they have their own personality.
Uh-huh.
We've talked about the reactive halogens,
Right.
the chill, noble gases, the in-between metalloids.
The multi-talented ones.
Exactly.
Yeah.
And even those heavyweights, the transuranium elements.
Yeah. Quite the variety.
It's been quite a journey. What other cool things are hiding in the periodic table?
Well, we've covered a lot. But there's always more to learn. Let's circle back to the noble gases.
Okay.
We talked about how they're unreactive.
Well, they're very zen.
Exactly. But there's more to the story. For a long time, they were considered completely inert. In fact, they were originally called inert gases. But then,
Yeah.
in the 1960s,
Okay.
a chemist named Neil Bartlett,
Okay.
he made the first compound containing a noble gas.
What? Really?
Yeah, it was xenon.
Wow, so the inert label was wrong.
Well, it wasn't entirely accurate, so how'd he do it?
Yeah.
Well, he knew that xenon, it's the heaviest of the stable noble gases.
Okay.
It has a low ionization energy. It doesn't take much energy to remove an electron from a xenon atom, compared to other noble gases. So he used a super strong oxidizing agent,
Okay.
platinum hexafluoride,
What?
to rip an electron away from xenon. And he created a compound called xenon hexafluoroplatinate.
Wow, that's a mouthful.
Haha, yeah. But it was a huge discovery.
It was. So did that lead to other compounds with noble gases?
It did. Since then,
Yeah.
chemists have made tons of compounds with xenon, krypton, and even argon.
So they're not completely inert after all.
Nope. They have a few secrets.
So even the most unreactive elements
Yeah,
can be surprising.
that's right. What are some of the applications for these compounds?
Yeah, I'm curious.
A lot of them are still mostly studied in labs,
Okay.
but some have real uses. For example,
Yeah.
xenon difluoride.
Okay.
It's used in the semiconductor industry for etching silicon.
So it's like even in these compounds, noble gases still kind of stay true to themselves.
What do you mean?
Well, they help things happen,
Yeah.
but they don't really get involved in the reactions.
I see what you mean. They're like the facilitators.
Exactly. Okay, we've almost reached the end of our deep dive, but I want to leave you with one last question.
Oh, okay. I like a good question.
We've seen how the properties of elements depend on their atomic structure.
Right, their electron configuration.
Exactly. But have you ever wondered what's inside the nucleus?
The heart of the atom.
Yeah.
It's a fascinating place.
I admit I've been so focused on electrons. I
Yeah.
haven't really thought about the nucleus itself. What's going on in there?
Well, the nucleus is made of protons and neutrons.
Okay.
And the way they're arranged,
Yeah.
how they interact, it determines if an element is stable or radioactive, and even its potential for nuclear reactions, releasing huge amounts of energy.
So there's a whole other level of complexity
Oh, yeah.
waiting to be explored.
There's always more to discover.
So even in an atom,
Yeah,
there are so many layers.
absolutely. This deep dive has been amazing.
It has.
Exploring the world of nonmetals and mixed groups. But it's just the beginning.
Wow, yeah. The periodic table. It's like a giant tapestry
I like that.
with each element a unique thread.
Weaving together the universe.
I'm leaving this deep dive with a new appreciation
Oh, yeah.
for the complexity and the beauty
Mm-hmm.
of chemistry,
Mm-hmm.
from hydrogen,
Yeah.
the simplest nonmetal,
Right?
to those massive transuranium elements.
Yeah,
Each one has its own story.
they really do. And who knows, maybe you'll be the one to discover something new, to push the boundaries of what we know about chemistry.
Thanks for taking me on this journey. It's been fascinating.
You're welcome. It's been my pleasure.
Until next time, I'll keep exploring and learning.
That's the spirit. Keep
Yeah.
that curiosity alive.